There is a wall inside every atom, and particles pass straight through it. Widen that wall from 1/10 of a nanometer to a full nanometer, a shift of only about 10 atoms laid side by side, and the chance of a particle crossing it does not simply shrink. It falls by nearly 10 orders of magnitude, a collapse of close to 1 billion-fold, from a small but real probability down to almost nothing at all. That is the width of maybe 10 atoms, and it is the difference between something happening and something never happening in the age of the universe. Hold that number in your mind. This is quantum tunneling, and it is the subject we are going to sit with tonight. It is the reason the sun burns. It is the reason the photos on your phone stay saved. It is a thing that sounds like a stage trick and turns out to be one of the most ordinary events in the universe, happening trillions of times a second inside the tips of your own fingers. If you enjoy following a strange idea all the way down until it lets you rest, consider subscribing to Deep Space Drift, and you can find these long quiet journeys on Spotify as well. That is the only time we will ask. Now let us begin. Start with the picture almost everyone carries. A particle, you were probably taught, is a tiny solid thing, a speck, a grain, a very small ball. It has a location, the way a marble on a table has a location, one spot and no other. And a wall in this picture is exactly what a wall should be. Something hard, something that stops you. So imagine rolling a ball toward a hill. The ball has a certain amount of energy, a certain speed. If the hill is low enough, the ball crests the top and rolls down the far side. If the hill is too tall, the ball slows, stops, and rolls back to you. This is the whole of classical physics in one image. Either you have enough energy to get over the barrier or you do not. There is no third option. A ball that cannot climb the hill never, under any circumstances, ends up on the other side. You have lived your entire life inside that rule. You lean on a wall and the wall holds. You set a cup on a shelf and it stays. Nothing you own has ever passed through anything else by accident. The rule feels less like physics and more like common sense, so deep in you that it barely counts as a belief. It is just how things are, and for objects your size it is exactly how things are. But the rule was never a law of the universe. It was only a very good approximation, one that holds beautifully for marbles and cups and human bodies, and quietly falls apart for the smallest things there are. Here is where the reveal begins. When physicists went looking at the scale of electrons and protons, they found that a particle is not a tiny solid ball at all. It does not sit at a single point. It does not have one fixed location that you could mark with a pin. Instead, a particle is described by something spread out, a wave. Not a wave in water, not a wave you could photograph, but a wave of probability, a smear of where the particle might be found. Physicists call this the wave function. It is the true description of the particle, and it obeys an equation written down by Erwin Schrödinger in 1926. Feed the Schrödinger equation the shape of the space a particle lives in, and it gives you back that wave, the full map of the particle's possible whereabouts. The wave is tall where the particle is likely to be. It is low where the particle is unlikely to be. And crucially, it is almost never zero anywhere. Sit with what that means. The particle does not have a location. It has a spread. It is, in a real physical sense, everywhere its wave reaches all at once until something measures it and pins it to one spot. Ask where the electron is, and the honest answer is a cloud, not a point. Now bring the wall back. In the old picture, a particle either had the energy to climb the barrier or it bounced off. But a wave does not climb anything. A wave does something stranger. When the particle's wave reaches the barrier, the wall it does not have the energy to cross. It does not stop dead at the surface. It does not bounce off like a ball off a fence. Part of the wave keeps going. Part of it enters the wall itself. Inside the barrier, the wave changes character. It stops being the rolling ripple it was in open space and becomes what physicists call an evanescent wave. That word, Evanescent means fading, vanishing, dying away. And that's exactly what it does. The wave still oscillates. It still carries the same energy it had before. But its height, its amplitude, drops fast as it presses deeper into the wall. It fades the way a shout fades in a room lined with thick padding. Quieter and quieter the further in you go, swallowed a little more with every step. If the wall is thick enough, the wave fades all the way to nothing before it reaches the far side, and the particle simply never crosses. But if the wall is thin, something remarkable happens. The wave, weakened, dimmed, nearly extinguished, still has a little height left when it reaches the far edge. And where the wall ends, that faint surviving wave straightens back out and becomes an ordinary rolling wave again, out in the open on the other side. A wave that comes out the far side of a barrier is a particle that has a real chance of being found there. Reduced, faint, but not zero. That surviving sliver of probability is the whole secret. The particle did not gather more energy. It did not smash through. It did not find a crack. It leaked, as a wave, through a wall it could never have climbed, and re-emerged on the far side with a smaller but perfectly real chance of simply being there. That is tunneling. A particle you thought was a hard little pellet turns out to be a soft spread of maybes, and a maybe can bleed through a wall that a pellet never could. Let me slow down on the strangest part because it deserves it. When the particle appears on the far side of the barrier, it does not appear tired. It does not arrive with less energy, as though it had spent something forcing its way through. It comes out with exactly the energy it went in with, and there is no record of it inside the wall. Nothing crossed the gap in the ordinary sense. There is no trail, no dented path, no moment you could point to and say, there. That is when it was halfway through. The particle was on one side, and then, with some probability, it is on the other. The space in between holds no evidence that anything passed at all. You can feel your mind reaching for a picture of it squeezing through, worming along some tiny tunnel in the material. Let that picture go. There is no tunnel despite the name. There is only a wave that was tall on one side, faint inside the wall, and rebuilt on the far edge. The word tunneling is a comfort we invented so the thing would sound like something we already knew. It is not really like anything we already knew. Now, if particles can do this, you might reasonably ask why the world looks so solid, why you cannot walk through your own front door. The answer lives in how sharply the odds fall, and it is worth understanding because it explains both why tunneling is everywhere and why you never notice it. There is a rule of thumb physicists use to estimate the chance of a particle tunneling. It carries the initials of the men who shaped it, Wenzel, Kramers, and Brillouin, so it is known as the WKB approximation. You do not need the mathematics. You only need its shape, and its shape is brutal. The probability of tunneling does not fade gently as the wall gets harder to cross. It falls off exponentially. That is the key word, and it changes everything. Exponential means the odds are strangled by three things and strangled fast. First, the width of the barrier. The thicker the wall, the deeper the wave has to fade before it reaches the far side, and each extra sliver of thickness cuts the surviving probability by another large factor. This is why moving a wall by the width of 10 atoms, from a tenth of a nanometer to a full nanometer, dropped the odds by that staggering 10 orders of magnitude we opened with. A tiny change in width, a billion-fold change in outcome. Second, the height of the barrier. The taller the wall, the more sharply the wave dies inside it, and again the penalty compounds. Third, and this is the one that saves your solidity, the mass of the particle. The heavier the thing trying to tunnel, the faster its wave fades in the wall, and the more hopeless the crossing becomes. Light particles like electrons tunnel readily. Heavier particles tunnel far less, and an object your size made of countless heavy particles at once has essentially no chance at all. So put those three together and you see why tunneling hides. For a single light electron facing a thin barrier, the odds might be poor but livable. It fails and fails and fails again, bouncing back almost every time. But almost every time is not every time, An electron in a solid can rattle against a barrier trillions upon trillions of times each second. And across that flood of attempts, the rare successes stop being rare in absolute terms. A 1 in a billion chance offered a trillion times a second becomes a steady, measurable stream. That is the quiet engine underneath so much of the physical world, not a single dramatic leap, but an ocean of failed attempts with a thin, reliable trickle of successes running through it. Each individual particle almost always bounces back. But there are so many particles trying so many times that the trickle adds up to real electric current, real reactions, real heat, real light. The wall is not being broken. It is being outlasted by numbers too large to feel. This is why the world looks solid to you and porous to an electron. You are one object trying, in effect, once, made of far too much heavy matter, facing far too thick a wall. The electron is one of an uncountable swarm, feather-light, facing a wall only a few atoms deep, trying again and again faster than you can form a thought. Same physics, same equation, wildly different worlds, separated only by size and by how many chances you get. And so you arrive at the sentence that should feel impossible and turns out to be true. A particle can vanish from one side of a wall it cannot cross, and appear on the other side with no trace of the journey in between. It does not tunnel through so much as it stops being only here and starts being possibly there. And the wall, however solid it looks, never had the final say. The barrier was never a barrier in the way you imagined. It was a place where a wave grew faint, and faintness, it turns out, is not the same as stopping. Everything else we will explore tonight grows out of this single strange fact. The sun overhead, the memory in your pocket, the clicks of a Geiger counter, the slow decay of heavy metals that took the age of the earth to unwind. Even in the faintest theoretical sense, the wall you could lean against forever, all of it is this same soft leak of probability through walls that should hold and do not quite. But before any of this had a name, it was only a puzzle buried inside a lump of decaying uranium, waiting for a young man in Germany to notice what it meant. But before any of this had a name, it was only a puzzle buried inside a lump of decaying uranium, waiting for a young man in Germany to notice what it meant. The young man was George Gamow. He was 24 years old. In 1928 he was working with Max Born in Göttingen, and he was staring at a riddle that the best physicists in the world had failed to crack. The riddle had a name. It was called radioactive alpha decay, and on paper it should not have been possible at all. Here is the thing they could not explain. Certain heavy elements, uranium among them, spit out small, fast fragments of themselves. Each fragment is an alpha particle, 2 protons and 2 neutrons bound together, a tiny chip of the nucleus flung out into the world. Physicists could catch these particles. They could measure exactly how much energy each one carried, and the number they measured made no sense. Think about what the alpha particle has to escape from. The nucleus it sits inside is packed with positive charge. The alpha particle is positive too. Like charges push each other away, and up close that push becomes enormous. It builds into a wall of repulsion that physicists call the Coulomb barrier. For a nucleus like uranium, that wall stands about 25 million electron volts tall. That is the height an escaping particle would need to clear. Now measure the particles that actually get out. They carry only about 4 to 9.5 million electron volts of energy. Read those two numbers side by side. The wall is more than 5 times taller than the particle is strong. The alpha particle is trying to climb a barrier it does not have anywhere near the energy to climb. Picture a marble trapped inside a deep bowl. The walls of the bowl are taller than you could ever throw the marble. Shake the bowl, rattle it. Wait as long as you like and the marble stays inside. That is what classical physics demands. A particle that weak, facing a wall that tall, should stay locked in the nucleus forever. It should never come out. And yet uranium decays. The particles come out anyway, For years, that was simply an impossibility that happened every day, sitting there unexplained. This is the puzzle Gamow picked up, and before we follow what he did with it, one small thing. If you find these quiet corners of physics worth an hour of your evening, a like or a subscribe helps more people find them, and helps this channel keep making them. That is all. Now, back to the wall that no particle should ever get past. Gamow's insight was to stop treating the alpha particle as a marble at all. In the new quantum mechanics he had been learning, a particle is not a hard little ball with a fixed spot. It is a spread-out wave of probability. It does not sit in one exact place. It is smeared across a range of places, some more likely than others, and a wave, unlike a marble, does not stop dead at a wall. Part of it soaks into the wall. Part of it can leak through to the far side. So Gamow asked a different question. He did not ask how the alpha particle climbs over the barrier. He knew it could not. He asked instead what fraction of its probability wave leaks all the way through the barrier and comes out the other side, and the answer was not 0. It was small, almost unimaginably small, but it was real. There was a genuine non-zero chance that the particle would simply be found outside the nucleus, having never had enough energy to be on top of the wall at any moment in between. That was the whole trick. The alpha particle does not smash through the barrier. It does not tunnel a crack and crawl out. It vanishes from inside and reappears outside, with no step where it was ever seen crossing the space between. One instant its wave is mostly trapped in the nucleus. The next, a faint sliver of that wave, and therefore a faint sliver of a chance, has surfaced on the far side of a wall it could not climb. Come back to the marble in the bowl and let the quantum version play out. The marble rattles against the walls. Almost every time it hits, it bounces straight back, exactly as you would expect. But once in an almost unthinkable while, the marble is simply outside the bowl. There was no leap. There was no moment where you saw it clear the rim. It was in, and then it was out, and the rules of the everyday world were quietly broken while nobody was looking. The alpha particle inside a uranium nucleus is doing exactly that, and it is doing it constantly. Trapped in that tiny space, it does not sit still. It moves. It rushes back and forth across the nucleus and slams into the inside of that barrier again and again. The rate of those collisions is hard to hold in your head. The particle throws itself at the wall on the order of 100 billion trillion times every second. 10 to the 21st attempts, each and every second for as long as the atom exists. Almost all of those attempts fail. The particle hits the wall and bounces back inside, hits and bounces, hits and bounces. Most of eternity for that particle is failure. But the escape probability is not quite 0. With that many attempts, the rare success eventually arrives. A single uranium-238 atom can sit there attempting to tunnel out 1 trillion times a second. For more than 4.5 billion years, the entire age of the Earth, before it finally succeeds even once. That is why uranium-238 has a half-life measured in billions of years. Its barrier is especially thick in wave terms, so the chance of leaking through on any one attempt is vanishingly small. Gamow was not alone in seeing this. In that same year, 1928, two other physicists, Ronald Gurney and Edward Condon, arrived at the very same explanation for alpha decay on their own. 3 people, working separately, all realized that nature was getting past a wall it had no classical right to cross. When an idea shows up in more than one mind at once, it is usually because the moment is ripe, and the moment for tunneling had come. The real proof that Gamow was right came from a pattern that had puzzled experimenters for years. It was called the Geiger-Nuttall law. Someone had noticed a strange link between two things. The more energetic the alpha particle an element throws out, the faster that element decays. The weaker the alpha particle, the longer the element takes. Nobody knew why that relationship existed. It was just a rule pulled from the data, with no reason behind it. Gamow's tunneling gave it a reason. A slightly stronger particle sees a slightly thinner wall to leak through, and because tunneling depends so steeply on the thickness of that wall, a small change in energy becomes an enormous change in decay time. And enormous is the right word. Look across all the alpha-emitting heavy elements, and the range of their lifetimes is staggering. Some decay in about 1/10 of a millionth of a second. Others take around 10 billion years. That is a span of 20 orders of magnitude from a flicker to nearly the age of the universe. Yet the energies of the alpha particles that come out vary by only about a factor of 2. A tiny change in the particle, a 20-0 change in the lifetime. That is the exponential fingerprint of tunneling, and once you see it in the numbers, it is unmistakable. Now step back from the equations and feel what Gamow had actually touched. This was not some obscure effect hidden away in a laboratory. It was already all around him, and it is all around you right now. Every click of a Geiger counter is an alpha particle, or one of its cousins having just tunneled out of a nucleus and struck the detector. Each click is one impossible escape made audible. Every radiocarbon date, every estimate of how old a bone or a piece of charcoal is, rests on the steady, clock-like rate at which unstable nuclei decay. That rate is set by tunneling probabilities. The reliability of the whole method comes from how faithfully particles leak through their barriers, at a pace that does not change. And the small radioactive source glowing quietly inside a household smoke detector is doing the same thing, sending out alpha particles that keep a tiny current flowing, particles that only exist outside their nuclei because they tunneled free. The moment smoke interrupts that flow, the alarm sounds. A wall crossing you never think about is standing guard over your home tonight. All of it, the clicks, the dates, the quiet glow, is quantum tunneling happening in real time. And it was seen for what it truly was, because a physicist barely out of university looked at an impossibility that everyone else had shrugged at, and refused to shrug. Hold that human scale for a moment. Not a greybeard at the end of a long career. A 24-year-old, only recently a student, doing the sort of thing that reshapes physics, and doing it because he was willing to take the strange new wave picture of matter, literally, all the way down. Imagine him at his desk in Göttingen. The nucleus he was thinking about is smaller than anything a human eye will ever resolve. A speck buried inside a speck. Inside it, an alpha particle is rattling back and forth at a speed and a frequency that no clock in the everyday world could follow, throwing itself at a wall countless times in the time it takes you to draw a single breath. Almost every throw is a failure, and in the failing, in the sheer stubborn repetition of it, hides the reason a lump of uranium can stay warm with slow decay for longer than the planet has existed. What Gamow held in his mind in 1928 was small enough to vanish inside an atom. But the loophole he had found was not small at all. He had shown that the universe keeps a door propped open, where classical physics swears there is only a solid wall. A particle without the strength to climb can still, now and then, be found on the other side. That single fact, that barriers are not truly absolute, was about to turn out to be one of the most important facts in all of nature. Because the same year Gamow was emptying a nucleus on paper, other physicists were beginning to wonder about a wall of a very different size. Not the wall around a single alpha particle, the wall between two protons trying to touch in the heart of a star. Overhead, in a furnace 93 million miles away, hydrogen nuclei were facing their own Coulomb barrier, their own impossible climb, and somehow fusing anyway to pour out light. The sun should have been too cold to burn. By the plain rules of collision and energy, it simply could not shine. And the escape hatch that would explain it was the very door Gamow had just found. Ronald Gurney and Edward Condon were not chasing fame that spring. They were chasing embarrassment. Radioactive decay had a rule nobody could explain, and it had been sitting there, unexplained, for years. Two men, working in Princeton, sat down with the same puzzle George Gamow was holding in Göttingen. They did not know about him. He did not know about them. And in that same year of 1928, both doors opened onto the same room. That almost never happens cleanly. An idea usually has one parent. This one arrived at two addresses at once, which is often how you can tell an idea was simply ready. The pieces were all lying on the table. Someone only had to see that the wall was not really a wall. Here is what they were staring at. Alpha particles come flying out of heavy nuclei. Measure their energy, and you find something modest, somewhere between 4 and 9.5 million electron volts. Then measure the barrier that is supposed to hold them in. For a nucleus like uranium, that electric wall stands around 25 million electron volts tall. The particle carries a fraction of the energy it would need to climb out. By every rule of ordinary physics, it should be trapped forever. It should never appear outside the nucleus at all. And yet there it is, arriving at your detector plainly free. So sit with that engagement for a moment, and if these quiet detective stories are the kind of thing you like falling asleep to, a like or a subscribe helps more people find them. You can find these on Spotify too. That is the whole ask. Now, the deeper mystery was not just the escape, it was a pattern in the escapes. Decades earlier, two experimenters named Hans Geiger and John Nuttall had noticed something while measuring one radioactive element after another. There was a relationship, clean and stubborn, between two numbers that had no obvious reason to be linked. Now, on one side, the energy of the alpha particle a nucleus threw out. On the other, how long that nucleus tended to survive before it decayed. Plot one against the other, and the points fell along a line. A little more energy in the escaping particle meant a dramatically shorter life for the parent. Geiger and Nuttall could see the rule. They could write it down. What they could not do was say why it was true. It was a law with no engine underneath it, a fingerprint with no hand. For years, it simply sat in the textbooks as a fact you memorized and did not question. That is the uncomfortable state a science lives in when it has a pattern but no cause. Watch what happens the moment you allow tunneling into the picture. Suddenly the whole curve makes sense, all at once, the way a scrambled photograph resolves when you finally focus the lens. The escape is not a leap over the wall, it is a slow leak through it. And the chance of that leak depends, with brutal sensitivity, on how thick the wall looks to the particle. A slightly more energetic alpha particle sees a thinner slice of barrier to pass through. A thinner barrier means an escape chance that is not a little higher, but enormously higher, because the odds fall off exponentially as the wall gets fatter. That is the trick of it. A small, gentle change in energy produces a colossal change in how long the nucleus lives. The Geiger and Nuttall line was not some strange coincidence of nuclear chemistry. It was the shape of an exponential, seen from the outside. It was tunneling, wearing a disguise, hiding in plain sight in data that had been collected before anyone knew what tunneling was. This is the part that makes the story feel like a solved case rather than a lucky guess. A good explanation does more than cover the fact you built it for. It reaches out and explains things it was never asked about. Gamow and Gurney and Condon did not set out to reproduce that old empirical law. They set out to explain how a single particle could escape a single nucleus. And when the mathematics was finished, the law fell out of it for free, uninvited, exactly matching numbers that experimenters had gathered years before. When an idea pays a debt you did not know it owed, you start to believe it is true. And the scale of what it explains is almost hard to hold in your head. Line up the alpha emitters by how long they live. At one end you find nuclei that decay in about 1/10 of a millionth of a second. At the other end you find nuclei that endure for something like 10 billion years. Between those two, the span is roughly 20 orders of magnitude. That is a 1 followed by 20 zeros, separating the shortest lives from the longest. Now here is the sentence that should stop you. Across that entire staggering range, the energy of the escaping alpha particles barely moves. It changes by about a factor of 2. That is all. Double the energy, more or less, and you slide across 20 orders of magnitude in a lifetime. Nothing describes an exponential more perfectly than that. A gentle nudge on the input, a monstrous swing on the output. The vast spread of nuclear lifetimes is not a sign of vast differences between nuclei. It is the fingerprint of a probability that is exquisitely, almost unreasonably, sensitive to the shape of a wall. Let one atom stand for all of it. Take a single nucleus of uranium-238. Its half-life is more than 4.5 billion years. That is not a poetic exaggeration. It is very close to the age of the Earth itself. The rock under your feet, the iron in your blood, the atoms that were forged in dying stars before the sun existed, and here is a nucleus whose personal clock is set to that same enormous span. Half of any batch of uranium-238 you could gather will still be sitting there, undecayed, patient, after all that time. And yet it is not idle in there. This is the detail that turns patience into something almost unbearable to imagine. Inside that nucleus, the alpha particle is not waiting quietly for permission. It is hammering at the barrier. It is rushing at the wall and rebounding, rushing and rebounding, on the order of 10 to the 21st times every single second. That is 1,000 billion attempts in the time it takes you to draw one slow breath towards sleep. Almost every one of those attempts fails completely. The particle throws itself at the wall, and the wall throws it back, again and again and again. The barrier is simply too thick, and the odds of leaking through on any one try are so faint they scarcely register as a number. So it tries again. And the arithmetic of that patience is the whole story of uranium. 1 trillion attempts per second, sustained for billions of years, and only then on average does one of them finally succeed. One leak, one escape, one click in a detector, an ocean of time later. That is what the Geiger and Nuttall line was quietly recording all along. Not the strength of the particle, not the height of the wall as such. It was recording how often a hopeless attempt, repeated with inhuman persistence, is allowed to win. A short-lived nucleus is one whose wall is just thin enough that the leak arrives quickly. A nucleus like uranium-238 is one whose wall is so thick that even 10 to the 21st tries a second must be stacked up for the lifetime of a planet before the exponential finally pays out. There is a strange comfort in how ordinary the resolution feels once you see it. For years the world had a rule and no reason. Then 2 ideas, born in the same season on opposite sides of an ocean, said the same simple thing. Let the particle be a wave. Let the wall be crossable, just barely, just sometimes. And the moment that was allowed, a curve that had been a mystery for a generation became the most natural thing in the world. The law did not need to be rewritten. It only needed to be understood. Gurney and Condon are barely remembered names now, spoken alongside Gamow when they are spoken at all, but they helped turn a memorized fact into a piece of understood nature. And the reason this matters far beyond a nucleus is that the same leak, the same faint permission to pass through a wall that should be solid, does not only let particles out of dying atoms, it also lets particles into places they could never otherwise reach. The physicists who first grasped alpha decay were sitting in ordinary rooms, in ordinary daylight, working out how a particle sneaks out of a nucleus. They may not have fully realized in that moment that they were describing sunlight itself. The very same trick that let a particle slip out of a nucleus was, in that moment, keeping the sun burning over their heads. The very same trick that let a particle slip out of a nucleus was, in that moment, keeping the sun burning over their heads. Think about what that means. The star that lights your mornings runs on the identical loophole. Not a metaphor, the exact same physics. So let us look up at the sun and ask a simple question. How does it actually shine? The answer is fusion. Deep in the core, hydrogen nuclei, which are just protons, are being forced together. When 2 of them finally bind, they begin a chain that turns hydrogen into helium and releases energy. That energy, over a long journey, becomes the sunlight on your skin. But there is a wall in the way. To fuse, 2 protons must get close enough for the strong nuclear force to grab them. The strong force is powerful, yet it only reaches across a whisper of distance, and both protons carry positive charge. Like charges repel. The closer you push them, the harder they shove back. That rising wall of repulsion has a name. It is the Coulomb barrier. Here is where the story should end. Because the Sun's core, by any honest accounting, is far too cold to climb that wall. A quick favour before we go deeper. If you find this quietly fascinating, a like or a subscribe genuinely helps this channel keep making these. We are on Spotify too for nights you would rather just listen. That is the whole ask. Now, back to the wall. Let us put real numbers on how cold the Sun actually is. The core temperature is about 15 million Kelvin. That sounds enormous. It is hotter than anything you will ever stand near. And yet, for fusion, it is nowhere near enough. Run the classical calculation. Ask what temperature you would need for 2 protons to slam together hard enough to overcome that Coulomb barrier by brute force. The number that comes back is staggering. You would need something close to 1 billion Kelvin, roughly 10 to the 9th Kelvin. That is the temperature required to fuse hydrogen at the rate we actually see. Hold that number in your mind. The Sun runs at 15 million Kelvin. It would need close to 1 billion. That leaves the core roughly 60 times too cold to do what it is plainly doing every single second. Sit with how strange that is. By the strict rules of classical physics, the Sun should not shine. The protons in its heart do not have the energy to reach each other. They should approach, feel the wall rise and be flung back over and over forever. No fusion, no helium, no light. A cold, dark ball of gas where a star should be. But the sky is not dark, so something in the classical picture is simply wrong. You already know what it is because you have watched it work inside the nucleus. The protons do not climb the wall, they tunnel straight through it. Remember what a proton really is. Not a tiny hard marble with a fixed spot in space. It is a probability wave, a smeared out cloud of where the particle might be found. When 2 protons approach, their waves do not stop dead at the Coulomb barrier. The wall thins their presence, fades it, but does not erase it. A faint edge of each wave leaks into the forbidden zone, and when 2 of those faint edges overlap, even slightly, even though the repulsion is officially keeping the particles apart, there is a real chance the strong force catches hold. Fusion happens, not over the wall, through it. The Sun shines because its protons are cheating a barrier they could never climb. They are borrowing the same loophole that let an alpha particle escape uranium. The engine of every star is quantum tunneling, hiding in plain sight. Now, before you decide this makes it easy, look at the odds, because this is where the Sun becomes almost unbelievable. Tunneling through the Coulomb barrier is not likely. It is absurdly, punishingly unlikely. Take any single pair of protons in the core, let them approach in one encounter, and ask the chance they actually tunnel and fuse. The estimate that comes back is around 1 in 10 to the 28th. That is a 1 followed by 28 zeros underneath it. One success buried in 10 billion tries. There is a comparison people reach for, and it barely does the number justice. Winning the Powerball lottery in 1 ticket is already a fantasy most people never touch. This is like winning the Powerball 3 times in a row. 3 separate jackpots, back to back, on the same run of luck. That is the rough chance that 2 given protons in the Sun's core will fuse when they meet. So we are left with a deeper puzzle than we started with. The Sun is too cold to fuse by force. And when it tries the quantum loophole instead, that loophole almost always fails. Almost every proton that gets close is turned away. The wall wins. Again and again, 10 billion times over. How does anything shine at all? The answer is not in the odds. It is in the sheer, overwhelming count of players. You beat impossible odds by taking impossible numbers of tickets. Picture the core of the Sun. Not as a place, but as a crowd. It holds on the order of 10 to the 57th protons. Write that out and it is a 1 with 57 zeros trailing behind it. A number with no meaning to human intuition. And every one of those protons is in furious, constant motion, colliding, approaching. being turned away, approaching again, billions upon billions of encounters every second across that entire boiling sea. When you have that many players buying that many tickets that many times, even a jackpot of 1 in 10 to the 28th gets won. Not once. Constantly. Enough proton pairs slip through the Coulomb wall every second to fuse hydrogen at exactly the rate that powers the sun's full output. The rarest event in the core, multiplied by the largest crowd you can imagine, becomes a steady, reliable furnace. That furnace is why you are warm. Every second, the sun converts millions of tons of matter into energy through these tunneling events. The light born from them takes about 8 minutes to cross the distance to Earth. So the sunlight touching you now left the core after a proton, against odds like winning 3 lotteries in a row, leaked through a wall it had no right to cross. 8 minutes ago, a coin that lands on its edge landed 10,000 trillion times over, and the glow reached your window. Let that settle over you slowly. There is no rush tonight. The sun has been doing this for 4.5 billion years, and it will keep doing it long after this thought has faded. You do not need to hold every number, just the shape of it. A wall no proton can climb, a wave that leaks through anyway, a crowd so vast that the impossible becomes routine, and now widen the frame because this is not only about our sun. Every star you have ever seen runs on this same trick. Every point of light scattered across the night sky. Every distant sun in every distant galaxy, out to the faint smudges at the edge of what any telescope can reach. All of them are too cold by the classical rules to fuse hydrogen in their cores. All of them shine only because their protons tunnel, so take the loophole away just as a thought. Imagine a universe with the same stars, the same hydrogen, the same crushing pressures at the hearts of suns, but no quantum tunneling, no leaking waves, no cheating the wall. In that universe, the Coulomb barrier stands unbroken. The protons approach and are flung back, always, everywhere. Not a single core gets hot enough to ignite, and so not a single star lights. The sky in that universe is truly black. No sunlight, no starlight, no warmth on any world, no chemistry rich enough for anything to wake up and wonder about it. Every star in the visible universe would stay dark and cold. The cosmos would be a place where nothing ever shines. The line between that dead universe and this living one is a single quantum effect, a subatomic loophole so small it took physicists until the 20th century to even suspect it. That is the strange gift hiding in the title. Particles walk through walls, and because they do, the sky's full of fire. It is worth pausing on how quietly this sat undiscovered. For all of human history, people watched the sun rise without any way to know why it burned. The answer was never in the heat we could feel, or the light we could see. It was in a rule of the very small, a rule that said a particle is a wave, and a wave can be faintly on both sides of a wall at once. The sun was keeping that secret the entire time. There is a certain peace in knowing it now. The warmth on your face has a lineage. It traces back through 8 minutes of empty space, down into a core 60 times too cold to work, to a proton that did the impossible because impossibility, at that scale, is only a matter of odds and patience. And the odds were beaten by a crowd of 10 to the 57th, buying tickets without pause since before the Earth had formed. You can feel your breathing slow as you follow it down. The wall, the wave, the leak, the light. It repeats in every star, in every galaxy, a rhythm older than the ground you stand on. For a long time, all of this was simply a fact of nature that humans could only observe from the outside. We could work out that the sun tunnels. We could write the equations, estimate the odds, marvel at the crowd of protons. But we were spectators. The loophole belonged to the stars and to the nuclei quietly decaying in the rocks beneath our feet. It was something the universe did, not something we could touch. That did not last. Because a curious species, having realized that the walls of physics have doors in them, does not stay a spectator for long. If a particle can slip through a barrier it cannot climb, then perhaps that trick could be aimed, harnessed, built into something. And once physicists understood the loophole that lights the stars, They began building machines that used it on purpose. I don't have a local file system available in this session to write to Brand's Claude from Agents Jan's DSD scripts, and the connectors that could persist a file, Google Drive, aren't the target path. Per the delivery rule, raw narration only, here is the finished pass for narration. And once physicists understood the loophole that lights the stars, they began building machines that used it on purpose. The first of them was a microscope that never touched the thing it was looking at. It was called the Scanning Tunneling Microscope, and it was built in 1981 by two men at an IBM laboratory in Zurich, Gerd Binnig and Heinrich Rohrer. 5 years later, in 1986, they were handed the Nobel Prize in Physics for it. What they had made was a machine that could feel a single atom by reaching out with nothing but a probability wave. Picture how it works, slowly, because the trick is in the gap. There is a needle, sharpened until its very tip narrows down to a single atom. That needle is lowered toward a surface, closer and closer, until it hovers just above it. Not resting on it, never resting on it. The gap it holds is about 5 to 10 angstroms wide, which is to say half a nanometer to a nanometer, a space thinner than the width of a few atoms stacked in a row. And across that empty gap, electrons begin to flow. They should not be able to. There is nothing bridging the space, no wire, no contact, only vacuum. By the old rules, the current should be zero. But electrons are waves, and their waves leak across the gap, and a tiny stream of them tunnels through the emptiness from tip to surface. That stream is the tunneling current. If you like this quiet corner of physics, a like or a subscribe helps more people find it, and Deep Space Drift is on Spotify too if you drift off before the end. Now settle back, and let us look at what that current can do. The current is almost impossibly small. It is measured in picoamps, in trillionths of an amp, a flow 1 trillion times fainter than the one feeding the bulb in a bedside lamp. It could not light anything. It could barely be called electricity at all. And yet, it is the most exquisitely sensitive ruler ever built, because the tunneling current depends on the gap in the harshest possible way. It falls off exponentially with distance. Move the needle away from the surface by just 1 angstrom, roughly the diameter of a single atom, and the current does not dip a little. It drops by a full order of magnitude. It falls to 1/10 of what it was. Think about what that hair trigger buys you. As the needle glides across the surface, every rise and dip beneath it changes the gap, and every change in the gap swings the current. A bump only 1 atom high slams the current down tenfold, so the machine simply listens to the current and traces the shape of the ground beneath the tip. It reads the surface 1 atom at a time, resolving detail finer than a single angstrom, drawing the invisible landscape of a crystal, as if running a fingertip over braille too small for any finger. On a screen, those atoms appear as rows of soft glowing bumps, an orderly egg carton of light, each swelling of brightness the electron cloud of 1 atom made visible. Nobody had ever seen this before. For all of human history, the atom had been an idea, a thing inferred, argued over, never looked at. The tunneling current turned it into a picture, and then the picture learned to move. In November of 1989, 2 IBM researchers, Donald Eagler and Erhard Schweitzer, used one of these microscopes not just to see atoms but to push them. On a cold nickel surface they dragged 35 individual xenon atoms into place, one by one, and arranged them into 3 letters. They spelled out the initials of the company that paid for the machine, IBM in atoms, each letter about 5 nanometers tall. It was the first time a human being had ever picked up single atoms and set them down where they were wanted. 4 years later, in 1993, IBM physicists went further. They took 48 iron atoms and stood them up in a ring on a sheet of copper. They called it a quantum corral. Inside that little fence of atoms, the electrons of the copper surface were trapped, and trapped waves do what all trapped waves do. They form standing ripples, still patterns of crest and trough, like the rings on the surface of a drum, and the microscope imaged them directly. For the first time, people were looking at the raw ripple of a quantum wave function. the probability itself rendered as a photograph. The same wave nature that lets a particle leak through a wall was sitting there in a ring of iron, holding still to be seen. So the loophole had become a tool, and the tool had become a camera pointed at the quantum world. But hold that thought about how faint this all is, a current too weak to warm anything, because the same faint effect is doing something in your pocket right now that has nothing to do with laboratories. Every photo you save, every song you keep, every file that survives after you switch the power off, lives inside flash memory, and flash memory runs on tunneling. Deep inside those chips are tiny structures called floating gates, little islands of conductor wrapped completely in insulation, sealed off on every side. To store a bit, the chip forces electrons to cross that insulation and land on the island. There is no door. The insulating layer is a wall the electrons cannot climb, so they tunnel through it. They pass through a barrier they have no classical right to cross, and once on the other side they are trapped, marooned on the island with nowhere to leak back to. That is all a saved bit is. An island with trapped electrons on it reads as one value. An island left empty reads as the other. Ones and zeros, written by shoving electrons through walls and pinning them there. Every text you have ever kept, every picture on your phone, is a pattern of electrons that once tunneled through the impossible and then stayed. Billions of them cross that barrier every time you press save. This was not an accident stumbled into by engineers. Tunneling had been deliberately engineered into hardware decades earlier. The very first device built on purpose to exploit it was the tunnel diode, made by Leo Esaki in 1957 and 1958. It earned Esaki a share of the 1973 Nobel Prize in Physics, alongside Ivar Gieva, who studied tunneling in superconductors, and Brian Josephson, who had predicted something stranger still. Josephson worked out, on paper, that pairs of electrons could tunnel together across a thin insulating slice caught between two superconductors. That prediction, that paired electrons could flow through a barrier as one, would carry the story all the way to the present, because in October of 2025 the Nobel Prize in Physics went to three men, John Clark, Mitchell Devereux, and John Martinis, for taking tunneling to a scale no one had thought possible. The old rule of thumb had always been that quantum weirdness belongs to the very small. A single electron can tunnel, a proton can tunnel, but surely a whole object, something you could hold in your hand, is far too big to behave like one quantum wave. These three men proved that rule of thumb wrong. Their prize was awarded, in the committee's words, for the discovery of macroscopic quantum tunneling and energy quantization in an electric circuit. The work reached back to experiments they had done at Berkeley in 1984 and 1985. What they built was a superconducting circuit, loops of material carrying current with no resistance at all, broken by those thin insulating slices Josephson had described, the Josephson junctions, and they cooled the whole thing down toward absolute zero, down to a few thousandths of a degree above it, a few millikelvin. That brutal cold was not for show. Heat is jitter, and jitter drowns the signal. Only by stilling nearly all the thermal noise could they see the circuit's true quantum voice, and when it spoke like a single particle. The circuit was large enough to see, large enough to hold, and yet it tunneled as one whole object, its state slipping through a barrier it should not have crossed. Stranger still was how its energy behaved. It did not climb and fall smoothly, the way anything in the everyday world does. Its energy came only in fixed steps, in discrete rungs, and the circuit jumped between them, flicking from one level to the next without ever pausing on the values in between. Quantized energy, in a thing you could put in your palm. The weirdness did not stop at the atom after all. It just needed the cold and the patience to show itself at human size. And that hand-size circuit was not a dead end. It was a seed. The very same Josephson junction technology from those 1984 and 1985 experiments is the direct ancestor of the superconducting qubits humming inside the quantum computers being built today by Google and by IBM. When you hear that a quantum computer holds a fragile state near absolute zero, this is the lineage. A prediction on paper, a diode, a microscope that felt atoms, a circuit that tunneled whole, and now machines that try to compute with the loophole itself. The thread runs unbroken from a needle hovering over nickel to the coldest engineered places in the universe. So there it is. The effect that lets a particle vanish through a nuclear wall also drew the first portrait of an atom, also spelled a name in xenon, also holds every photograph you own, and in 2025 was crowned again for behaving itself at a scale you can cradle in one hand. It is not a curiosity hidden in equations. It is infrastructure. It is the quiet machinery under the ordinary surface of your life, working in picoamps and millikelvin while you never notice. And yet, for all these machines, for the microscope and the memory chip and the Nobel-winning circuit, the finest instrument that runs on tunneling was never assembled by any of them. No engineer designed it. No laboratory cooled it. It writes and rewrites itself, warm and unlit, folding the same impossible passage into the chemistry of a living thing. That same exquisite sensitivity had one more secret folded inside it. The tunneling current across the microscope's tip does not only measure a surface, it can also grip it. Bring the needle close enough, within 5 to 10 angstroms of the metal, less than a single nanometer, and the faint bridge of tunneling electrons begins to behave like an invisible thread. Nudge the tip sideways, and a lone atom sitting on the surface can be coaxed to follow it along. The very tool that let you see one atom could now be used to move it, deliberately, to a chosen spot. In November of 1989, 2 researchers at IBM's laboratory in California set out to see how far that idea could be pushed. Their names were Donald Eigler and Erhard Schweitzer. They chilled a clean sheet of nickel down toward absolute zero, colder than the darkness between the planets, to hold every atom perfectly still. Then they scattered a thin dusting of xenon atoms across it. One at a time, with the microscope tip, they dragged those atoms into position. 35 xenon atoms in all. When they finished, the atoms spelled 3 letters. I, B, M. Each letter stood about 5 nanometers tall, so small you could line up thousands of these logos across the width of a single human hair. It was the first time in history that human beings had deliberately arranged individual atoms, one by one, exactly where they wanted them. The result was published in the journal Nature in 1990, a photograph of a company's name written in the smallest ink that will ever exist. Think about what that photograph truly was. Not paint, not etching, not a mark pressed into a surface. Just atoms, set down like stones in a garden, each held in place by the cold and the careful geometry around it. And every step of it ran on tunneling. The tip never touched the nickel. It hovered above, close enough that electrons could leak across the empty gap with no wire to carry them, a current so faint it could not light the dimmest bulb, measured in trillionths of a single amp. That whisper of current was the only thing telling the machine where the surface lay and where each atom sat, precise to a fraction of an atom's width. 4 years later, the same laboratory did something stranger still. In 1993, the team arranged 48 iron atoms into a perfect ring on a sheet of copper. They called it the quantum corral, a tiny fence built entirely from single atoms. And a fence, on that surface, does something remarkable. The electrons drifting freely across the copper cannot easily cross the ring of iron. They pile up against it from the inside, and they behave, as electrons always do, like waves. When a wave is trapped inside a circular pen, it does not slosh at random. It settles into standing ripples, still rings nested inside the outer ring, frozen crests and troughs of pure probability, and the microscope could see them. When the team scanned the floor inside their corral, the image that came back was not flat. It was a set of concentric ripples, like the surface of a pond caught mid-quiver and held there forever. Those ripples were not water and not metal. They were the shape of the electron's own probability, the wave function itself made visible. For decades that wave had been an abstraction, a term in an equation, a thing you were told existed but could never point to. Here it was, photographed at last, a direct picture of the ghostly spread that lets a particle be in many places at once. The corral had caught the wave and held it up to the light. Every part of that image, once again, was tunneling, the same exponential rule that makes the microscope so sharp. The way the current climbs or falls tenfold for every single atom's width, the tip rises or drops, is what let it trace those faint ripples without ever brushing them. The machine read the height of a standing wave that was itself barely there, by counting electrons that classical physics says should never have reached the tip at all. Then, in 2013, IBM carried the whole thing one step past science and into cinema. Its researchers set out to make a movie, not a movie about atoms, a movie made of them. They used the microscope to nudge individual carbon monoxide molecules across a surface, one at a time, arranging them into a small figure, a boy with a single bright dot beside him that stood for his own atom. Then they shifted the molecules a little and captured another frame, then again and again. Frame by frame, molecule by molecule, they built a stop-motion film the way an animator builds one from clay, except here the clay was single molecules and the stage was a patch of metal a few atoms across. The finished film was called A Boy and His Atom. It runs about a minute. The boy bounces, dances, and plays catch with his lone atom. It was certified as the smallest movie ever made, its actors magnified more than 100 million times just to be seen at all. Picture that on a screen. The boy is not a drawing. Every part of him is a placed molecule, rendered by the microscope as a soft glowing bump, a row of atoms that looks like an orderly carton of light, each little mound of brightness a single electron cloud caught in the faint gleam of a tunneling current. Nothing about him was painted. He was assembled, atom by atom, then rearranged and photographed, hundreds of times over, so that the smallest things we know how to touch could be made to move like a cartoon. And consider the range of conditions this one trick can span. The scanning tunneling microscope will work in the deepest cold, below 4 Kelvin, only a few degrees above absolute zero, where atoms sit so still you can pin them in place like insects. And it will keep working when the surface is heated past 973 Kelvin, hotter than molten lead, the atoms shivering with heat, and still the current holds steady enough to read them. Across a span of temperature wider than almost anything in ordinary life, the same faint leak of electrons keeps telling the machine exactly where the surface is, down to less than a single atom's width. That is the quiet astonishment buried in all of it. Writing a company's name in atoms, photographing the raw shape of a wave function, animating a boy built from single molecules, none of it required a new law of physics. It needed only the oldest trick in this whole story, the one where a particle slips across a gap it has no right to cross. The engineers simply learned to aim it. They took the same exponential shyness of the tunneling current, its almost unbelievable fear of distance, and turned it first into the steadiest ruler ever made, then into a pen, then into a camera. A phenomenon that once explained why the sun burns and why atoms hold their shape had been quietly tamed into a drawing tool, patient enough to spell, to portray, and to animate, one atom at a time. So tunneling has been photographed. It has been written with. It has been used to make the world's smallest film and to lift a single wave function into plain sight on a screen. It has been built into microscopes and diodes and the memory in your pocket, engineered, refined, and honoured with its share of Nobel Prizes. Reach into your pocket. The phone resting there has stored every photo you have ever saved using this exact effect. Not a cousin of it, not a metaphor for it, the real thing. Electrons walking straight through a wall, billions at a time, on command. Inside the memory chips sits a structure called a floating gate. Think of it as a tiny metal island. That island is sealed on every side by an insulator, a layer of oxide that no electron is supposed to enter. The oxide is a wall, and a good one. By the ordinary rules, an electron reaching its face should simply stop. The oxide is also absurdly thin, only a few atoms thick, 10 atoms give or take, standing shoulder to shoulder, and you already know what happens to a barrier when it gets that thin. It stops behaving like a barrier. The exponential math that governs tunneling turns a wall of a few atoms into something an electron can slip across, given a push. So the chip gives it a push. When you hit save, it drives a strong voltage across that oxide, and electrons leak straight through it. They do not climb over the top, they do not squeeze through a crack, because there is no crack. They tunnel the very same way a proton tunnels out of a uranium nucleus, and they arrive on the floating island waiting on the far side. Once there, they are trapped. The oxide that let them cross under high voltage becomes a solid wall again the instant that voltage drops away. The electrons settle onto the island with nowhere to go. They can sit there for years, in a good chip, for decades. That trapped charge is your data. That is the entire secret. A floating island crowded with trapped electrons reads as one value. A bare island swept clean reads as another. Charge present, charge absent, a 1 and a 0. Every letter of every message you have kept, every frame of every video, every song in your library is written as a pattern of these islands, some holding a small puddle of electrons that walk through a wall, some left empty. Reading a bit is the gentle part. The chip does not disturb the trapped electrons at all. It only asks whether they are there. The charge on the island tilts the current running through a nearby channel, and the chip listens for that tilt, present or absent. It reads the ghost without ever touching it. Erasing pulls the electrons back the way they came. Another strong field, this time reversed, and the trapped charge tunnels back out through the same few atoms of oxide. The island is wiped clean, ready to be written again. Write, read, erase. Every step but the reading is a tunneling event you triggered on purpose. Now hold the scale of it in your mind. A single modern memory chip holds trillions of these gates. Fill your phone with photographs and you have coaxed a number of electrons across those walls that has no comfortable name. It happens every time you tap the shutter, every time a text arrives at midnight and is still sitting there when you wake. Every save is a small, silent flood of particles doing the classically impossible, quietly, reliably, exactly on schedule. The same thing is happening in the USB drive in your bag, in the solid-state disk inside your laptop, in the card inside a camera. All of it. The same floating islands, the same few atoms of oxide, the same electrons tunneling on demand. That is worth sitting with for a moment. The word tunneling sounds like a rare event, a thing that happens once in the heart of a star or deep inside a decaying atom. But it is not rare at all. It is one of the most common events in your ordinary day. Your saved messages depend on it. Your stored pictures depend on it. It is running in your pocket right now while the room is quiet. The floating gate is a modern refinement of the idea, but the first device built on purpose to use tunneling came much earlier, and it came out of a single stubborn measurement that refused to make sense. In 1957 and 1958, a physicist named Leo Esaki was studying heavily doped semiconductors in Japan. He noticed something backward. As he raised the voltage across a certain junction, the current went down instead of up. That should not happen. In an ordinary component, more push means more flow. Esaki was watching flow shrink as he pushed harder. He worked out what he was seeing. He had built a junction so thin and packed so densely with charge that electrons were slipping directly across the barrier rather than climbing it. At 1 voltage, the tunneling was strong and the current was high. Nudge the voltage further and the crossing points fell out of alignment and the current dropped. That falling current, that stubborn backward behavior, was the fingerprint of the effect, so he turned it into a component, the tunnel diode. It was the first semiconductor device engineered from the very start to exploit electron tunneling rather than to fight it. It was fast, faster than the electronics around it, because the crossing itself is nearly instant. For years, engineers had treated tunneling as a nuisance, a leak, a flaw to be sealed off. Esaki treated it as the whole point. The idea spread quickly, and it climbed to the top of the field. In 1973, the Nobel Prize in Physics was split 3 ways, and every one of those 3 shares was about electrons walking through walls. Esaki took 1 share for the tunnel diode, for tunneling inside a semiconductor. Ivakieva took a share for showing the same effect across superconductors. He cooled metals until they lost all resistance, set a thin insulating gap between them, and measured electrons tunneling across that gap. From what could slip through and what could not, he mapped out the hidden energy structure of a superconductor. The 3rd share went to Brian Josephson. He was still a graduate student when he did the work. He predicted on paper that pairs of electrons could tunnel together across a thin insulating barrier between 2 superconductors. Not one electron alone, a bonded pair crossing as a single unit in a delicate coordinated leak. Some people doubted him. The effect seemed too subtle, too strange to survive contact with a real experiment. Then it was measured, precisely as he had described it. That prediction is now called the Josephson effect, and the thin insulating gap at its heart is called a Josephson junction. Hold on to that name, it matters more than it looks. The Josephson junction is the beating component inside the hand-sized circuit that won its own Nobel Prize decades later, the one that made a whole object tunnel as a single thing. The paired electrons Josephson imagined slipping across a gap became the foundation of that machine. They are also the foundation of the superconducting quantum computers being assembled right now. So the effect has a lineage you can trace with your finger, a backward current on a lab bench in the late 1950s, a 3-way prize in 1973, a floating island of trapped charge in the phone you're holding tonight. One idea, carried forward, hidden in plain sight the whole way, and that is the quiet lesson underneath all of it. An effect that sounds like a magic trick turns out to be a workhorse. It is not exotic. It is not fragile. It is the hourly mechanism behind every saved photo and every kept message. The reason the words you type today will still be waiting for you tomorrow morning. Something that should be flatly impossible has become one of the most dependable things in your life. So dependable that you never think about it once. You carry it everywhere. In your pocket, in your bag, in the little chips scattered through your home, holding your memories on islands of trapped charge. Particles doing the impossible over and over, so ordinary now that it fades into the background hum of an ordinary day. But the strangest machine running on this effect was never built in any lab because it was already humming quietly inside you. File path intended, Claude, agents, DSD, scripts, quantum tunneling.md's pass4 could not be written. No file system tool is exposed in this session. The narration above is the deliverable. Word count, 1,560 words. Pre-flight, this pass, opens on exact thread sentence. Pass, ends on exact handoff sentence. Pass, phrase to budget, sleep well tonight. 0, good night. 0, pass, neither used. No dashes as punctuation. Pass, ASCII. Only, pass. No headers, timestamps, markers. Pass, covers full outline. STM, Binig Rora, 1986. Mechanism picoamps 1 angstrom order of magnitude. IBM logo, Quantum Corral, flash memory. Esaki 1973, 2025. Clark Deverett Martinis, Josephson junctions, millikelvin gas quantized jumps, qubit ancestry, inward turn. Pass, 1 engagement beat, 50 words. After opening, pass, word budget 2400, within 10%, 2160 a min. Fail, came in 160, roughly 840 short of the 2400 target. I flagged the shortfall rather than padding with filler. If you want, I can expand to hit 2060, 2400 by deepening the STM section. Temperature range below 4K to above 973K, the 2013 A Boy and His Atom film, more on the Corel standing waves, and the flash qubit mechanism keeping the same open and close. Want me to extend it? But the strangest machine running on this effect was never built in any lab, because it was already humming quietly inside you. It is running now, in the dark, in every cell you carry. Deep in your chromosomes, 2 strands of DNA wind around each other like a twisted ladder. Each rung of that ladder is held together by hydrogen bonds, and sitting in the middle of each bond is a single proton, 1 hydrogen nucleus, shared between 2 chemical letters like a hand held across a narrow gap. That proton is not nailed in place. It sits in a small energy valley, closer to one base than the other, and by every rule of ordinary chemistry it should stay there. But in 1963, a Swedish physicist named Per-Olof Laudin looked at that arrangement and saw something else. He proposed that the proton could tunnel. It could leak across the hydrogen bond and settle on the wrong side, without ever having the energy to climb over. When it does, the letter it belongs to changes shape. Chemists call these rare alternate forms tautomers. A base that should read as one letter now, for a flickering moment, reads as another. Most of the time this means nothing. The proton drifts back, the letter reverts, and the code stays intact. But there is one moment when it matters more than any other. Before I take you deeper into your own cells, one small thing. If these quiet journeys through physics help you sleep, a like or a subscribe tells the channel to keep making them, and you can find every episode on Spotify too. That is all. Now let your breathing slow and stay with me. The moment that matters is replication. When your cells divide, an enzyme called DNA polymerase runs along the ladder, reading each rung and building a matching copy. It works with astonishing accuracy. But if it arrives at a rung in that rare tautomeric state, in that flickering wrong form, it can misread the letter. It pairs the base with the wrong partner, and then it moves on, locking the mistake into the new strand. That error does not fade. It becomes a permanent point mutation, copied forward into every cell that descends from this one, written into the heritable code you might one day pass on. A single proton, leaking across a gap it had no classical right to cross, can quietly author a change in the book of life. For a long time this was only an idea, elegant but unproven. How could anyone tell whether a proton was truly tunneling, rather than simply being jostled over the barrier by ordinary heat? The answer came from the one thing tunneling is exquisitely sensitive to: mass. Tunneling probability depends steeply on how heavy the particle is. A slightly heavier particle tunnels far less readily through the same wall. So researchers ran a clean test. They replaced the ordinary hydrogen in DNA's environment with deuterium, a heavier form of hydrogen carrying an extra neutron. If the proton were merely hopping over the barrier by thermal energy, swapping in a heavier version would change little. But if it were tunneling, the heavier particle should slow the whole process down in a measurable way. That is exactly what happened. Work from the quantum biology group at Surrey found that the heavier isotopes slowed the tautomer transition. The effect was mass-sensitive, which is the fingerprint of tunneling and not of simple heat. And when the numbers were worked through, the tunneling contribution to the proton transfer ran orders of magnitude above what classical hopping over the barrier could produce. The wall was not being climbed, it was being passed through. Now, one honest caution before you drift too far into wonder: that tunneling helps flip these letters is well supported. But how much of your total mutation load it accounts for, set against copying errors, radiation and chemical damage, is still openly debated. Nobody claims tunneling is the main author of mutation. It is one quiet contributor among several, and the exact size of its share is still being measured. Hold that lightly, the way you would hold anything not yet settled. But DNA is not the only place your body uses this trick. Consider the enzymes that keep you alive, the tiny molecular machines that run nearly every reaction in your cells. Many reactions face an energy barrier, a hill that molecules must somehow get over before they can react. Ordinary chemistry says you supply enough heat and shove them over the top. Enzymes found a better way. An enzyme's active site is not rigid. It flexes and squeezes, folding around the molecules it works on and pressing them together. That conformational squeezing shortens the distance a proton or an electron has to travel. And once the gap is thin enough, the particle does not need to go over the barrier at all. It tunnels straight through it. Picture a tiny slingshot pulling two atoms so close that a proton simply leaks from one to the other, rather than being thrown over the wall between them. This is now considered essential to explaining how enzymes reach their extraordinary speeds, accelerating reactions by factors that classical chemistry alone cannot account for. The whole field has a name: quantum biology. It treats tunneling not as a subatomic abstraction locked away in physics labs, but as a working, living part of the chemistry inside you, in your DNA, in your enzymes, in the machinery that lets you draw your next breath. So here is a strange truth to rest on for a moment. The same effect that lets particles escape the heart of an atom is at work inside your own cells, right now, quietly and constantly. You are not separate from the quantum world. You are built from it, held together by it, and gently rewritten by it. Which raises the question you've probably been waiting for. If particles walk through walls, and if you are made of particles, then why can you not walk through a wall yourself? Why does the door stay a door, and the floor stay the floor? The honest answer is stranger than a flat no. The equations of quantum mechanics do not forbid it. Macroscopic tunneling, an entire solid object passing through a solid barrier, is technically permitted by the same math that governs the proton in your DNA. The equations never quite close that door. They only make it almost impossibly heavy to open. Here is why. Tunneling probability shrinks exponentially as mass increases, and it shrinks with the number of particles involved. A single proton has a real chance, but a solid object is not one particle. Take a tennis ball. It contains roughly 10 to the 25th atoms. That is a 1 with 25 zeros after it. Hold that number in your mind. For the ball to pass through a wall as a whole, every one of those atoms would have to tunnel through, in the same direction, at the very same instant. The chance of one particle tunneling is small. The chance of all of them doing it together, in perfect unison, is a number so close to zero that it stops meaning anything. Physicists like Brian Cox and Brian Greene have put it in plain terms. Imagine you walked up to a wall and tried to pass through it once every second. Imagine you kept trying once a second for the entire age of the universe, about 13.8 billion years. Even then, the expected number of successes would still be effectively zero. You should not expect it to happen even once. This is not a matter of scientists failing to try hard enough. It is untestable in principle, because the odds outrun any timescale we could ever observe. The comparison people reach for is lottery odds stacked upon lottery odds. It is like flipping a coin and having it land on its edge, balanced on another coin also on its edge, and repeating that for longer than there has been a universe in which to repeat it. So the wall holds. Not because the physics forbids you, but because the physics makes the waiting longer than forever. And that is a gentle thought to lie with. The very same effect that leaks an electron across a microscope's tip and flips a letter in your DNA is what keeps your body solid and whole. The improbability that traps particles inside atoms is the improbability that keeps you from falling through your own bed. You are held here by the sheer weight of numbers. But there is one last place this idea reaches, and it is the largest place of all. Not inside you, and not through a wall, but at the edge of reality itself. Some physicists model the universe's own vacuum, the empty space that everything sits in, as something that may not be truly empty or truly final. In this picture, governed by the Higgs field, space rests in what is called a false vacuum. It feels stable. It has felt stable for 13.8 billion years. But it may not be sitting at the lowest possible energy. There may be a deeper valley beneath the one we are in, a true vacuum, lower still. When physicists take the standard model, our best theory of particles, and extrapolate it to enormous energies, they find something that should make you sit very still. The universe appears to be balanced right at the edge between stability and metastability. not clearly safe, not clearly doomed. Poised on the line between the two, in a way that depends on precise values of the Higgs and the top quark that we have not yet pinned down. And if the vacuum is only metastable, then quantum tunneling has one more role it could play. Somewhere, someday, a tiny bubble of true vacuum could nucleate. It could tunnel into existence out of nothing, the way a proton tunnels through a wall, and once it formed, it would not stay small. It would expand outward at nearly the speed of light. Inside that bubble, the fundamental constants of physics would be different from our own, and the reality we know would simply be rewritten as the wall of the bubble swept past. There would be no warning. Because the bubble travels at nearly light speed, nothing could outrun it to tell you it was coming. No signal, no flash, no sound. The change would arrive at the same instant you learned of it, which is to say, you would never learn of it at all. Let that settle without fear, because here is the part that matters most. Even if the vacuum is metastable, the calculations say the chance of such an event happening anywhere in the observable universe, on any timescale that touches a human life, is vanishingly unimaginably small. This is a live hypothesis, not a settled fact, and it hangs on measurements we have not finished making. It is a curiosity at the far edge of physics, not a shadow over your night. You are astronomically safer than you are in any danger. So sit for a moment with the shape of all this. The same quiet phenomenon that lets the sun shine, that stores the photos on your phone, that flickers inside your own DNA, is also the thing that, in principle, permits a person to walk through a wall and permits a bubble to unmake the cosmos. All of it from one idea. Particles are waves, and waves do not stop cleanly at walls. And here is the paradox to carry into sleep. The very physics that keeps you solid, that holds your atoms in place and your DNA intact, is the same physics that quietly declines to forbid the impossible. It does not promise you can never pass through the wall. It does not promise the universe will stand forever. It only makes those things so rare that the whole history of everything is not yet long enough to see them happen. That is the deep strangeness at the bottom of reality. It is not built on hard walls and firm no's. It is built on probability, on almost and on nearly, on doors that are never truly locked, only weighted with odds too vast to lift. There is a second uncertainty hiding inside the first, and it has nothing to do with whether a particle tunnels. It has to do with how long the crossing takes. You would think this is a simple question. A particle goes in one side of the barrier and comes out the other, so surely you can put a clock on it. But when physicists actually try, the clocks disagree with each other, the numbers do not line up, and some of the numbers come back at zero. Think about what zero would mean here. It would mean the particle spends no time at all inside the wall. Not a brief moment, not a flicker, but nothing. It is on one side, and then it is on the other, with no measurable interval in between. A handful of early experiments hinted at exactly this, and the hint alone was enough to start an argument that is still running. The trouble is that you cannot simply watch. The inside of a barrier is the one place a particle is never supposed to be found, so you have to be clever about how you time it. Physicists built several different clever methods, and each one asks the question in its own way. One approach is called the attaclock. It uses a spinning electric field, a little like the sweep of a second hand, and reads the angle at which a tunneling electron finally emerges. The angle becomes the time. When researchers ran it, some results came back suggesting the electron crossed almost instantly, close to no delay at all. That single finding is where much of the excitement and much of the doubt began. Another approach is called the llama clock. Here the timekeeper is the particle itself. A particle has a tiny internal spin, and that spin turns at a steady rate when a magnetic field is present. So you put a weak field inside the barrier and measure how far the spin has rotated by the time the particle comes out. The amount of turning tells you how long it lingered. It is an elegant idea. You are letting the particle carry its own stopwatch through the wall. A third family of methods uses streaking, where a fast laser pulse smears the outgoing particle across a detector so its arrival time can be reconstructed from where it lands. Each of these techniques is careful, each is respected, and each has, at times, returned an answer that does not match the others. That is the heart of the controversy. It is not that the experiments are sloppy, it is that they may be measuring subtly different things and calling them by the same name. When you say tunneling time, you might mean the moment the particle enters, or the moment it exits, or the delay compared to a particle that faced no barrier at all. These are not obviously the same quantity, and when the methods disagree, you are left wondering whether the disagreement is in the apparatus or in the question itself. In May of 2024, a group of physicists in Darmstadt pressed on exactly this point. They argued that a number of the earlier tunneling time measurements had been carried out incorrectly, and that the field needed a new and more careful methodology before anyone could trust the headline results. Their claim was not that tunneling is slow or fast, but that the community had not yet earned the right to say. It was a call to slow down and rebuild the foundations. So when you read that a particle tunnels faster than light, or that the crossing happens in 0 time, hold that lightly. Those phrases come from real data, from real instruments, and they are genuinely fascinating. But they are contested. They are not the settled view. The more honest statement is smaller and stranger. Physicists agree completely on whether tunneling happens. They cannot yet agree on whether it takes any time to happen, or whether the duration is even a real property of the world rather than an artifact of how you choose to ask. That is a remarkable place for a mature theory to be. The equations that predict tunneling are among the most tested in all of science. They power the sun over your head and the memory in your pocket, and when you turn to them and ask a plain question, how long, they do not hand back a single clean number. They hand back a debate. Now let that question grow. Take the same quiet mathematics that lets a particle slip through a wall and point it not at an electron but at the entire universe. Because tunneling in principle does not only move particles, it can move the vacuum itself. Empty space is not nothing. It has an energy set by the fields that fill it, and in particular by the Higgs field. You would like to believe that empty space sits at the bottom of its own valley, at the lowest energy it could possibly have, perfectly and permanently stable, but it may not. It may be resting in a valley that only looks like the bottom. There could be a deeper valley somewhere below, a true lower state, with our current vacuum merely paused above it. Physicists call the false version a false vacuum, and the deeper one a true vacuum. Whether we live in one or the other is not a matter of taste. It comes down to numbers, 2 numbers mainly, the mass of the Higgs boson and the mass of the top quark, the heaviest particle we know. Feed the best measured values into the standard model and extend the math up to enormous energies, and the answer lands right on the fence. Not clearly stable, not clearly doomed. Balanced almost exactly on the edge between the two, so close that the small remaining uncertainty in those masses is enough to tip the verdict either way. Sit with how delicate that is. The long-term fate of empty space may hinge on whether the top quark is measured a little heavier or a little lighter than we currently think. We are not confidently safe, and we are not confidently condemned. We are perched on the boundary, waiting for sharper instruments to tell us which side we're on. If the vacuum truly is the false kind, then the same loophole that frees an alpha particle from a nucleus applies to space itself. Somewhere, at some point, a tiny bubble of the true vacuum could tunnel into existence. Inside that bubble, the constants of physics would be different. The rules that hold your atoms together might not hold there at all, and the bubble would not sit politely. It would expand, its wall racing outward at nearly the speed of light, rewriting everything it swept across into the new physics inside. The unnerving part is the silence of it. Because the wall moves at almost light speed, nothing could outrun it to warn you. No signal, no flash, no tremor could arrive ahead of the change. There would be no sky darkening, no sound. The old universe would simply end at the edge of the bubble, and you would never see it coming, because seeing it coming would require light to travel faster than the thing itself. That is the picture that gets repeated in dramatic terms, and it is worth being calm and exact about it. Even if the vacuum is metastable, the odds of such a bubble forming anywhere near you, on any timescale that touches a human life, or a civilization, or the current age of the universe, are estimated to be vanishingly, almost unimaginably small. This is not a forecast. It is not something to fear tonight or any night. It is a consequence that the mathematics permits, filed at the very far end of possibility, far past forever. And notice what these two questions have in common. One is as small as a single electron slipping through a nanometer of wall. The other is as large as the fate of all of space, yet they rhyme. In both cases, the underlying equations are confirmed, trusted, checked against experiment again and again, and in both cases, when you ask them for a clean answer, they decline. How long does tunneling take? Is the vacuum stable? The same well-established mathematics that gets so much exactly right will not, on these 2 points, close the case. That refusal is not a flaw. It is the reason the work continues. It is why there are physicists in Darmstadt rethinking how to time a particle, and physicists at colliders shaving the uncertainty off a quark mass, chasing that one last digit that might tell us which valley we live in. The theory is precise enough to raise the question, and honest enough to leave it open. It points to a place, marks it clearly, and then admits it does not yet know what waits there. So the strangeness that runs through all of this, from a proton in the sun to the edge of the vacuum, comes down to a single quiet habit of the mathematics. It deals in probabilities, not certainties. It leaves doors unlocked that common sense insists should be sealed. The equations never quite say never, and that is the thought to carry with you now into the quiet. The equations never quite say never, and that is the thought to carry with you now into the quiet. Solidity, it turns out, was never a promise. It was only a probability, and a very good one. The wall in front of you holds because the odds are on its side, not because the universe forbids anything else. Every atom in your hand is mostly empty space, held in place by rules that bend but almost never break. You are steady tonight because the numbers are steady. Think about what that really means. The floor beneath you does not stop your foot because passing through is impossible. It stops your foot because passing through would require every one of your roughly 10 trillion atoms to leak past the barrier at the very same instant. That is why a tennis ball never drifts through a table, and why you have leaned against 1,000 walls without once falling out the other side. The loophole is real. It is simply too narrow for anything as large as a person to fit through in all the time there has ever been. Hold that number in your mind. Once a second for the entire age of the universe, nearly 14 billion years, and you would still not expect to pass through the wall even once. That is not a failure of patience. It is the shape of the odds themselves. And yet the same faint loophole that keeps you out of the wall is everywhere else, quietly saying yes. It is the reason the sky is not dark. The sun's core burns at 15 million Kelvin, far too cold to force its protons together by brute collision. They only fuse because they tunnel, slipping through a wall of repulsion they could never climb, at odds near 1 in 10 to the 28th per meeting, redeemed only by the unthinkable number of protons crowded into that heaving core. Somewhere in a heavy nucleus, an alpha particle presses against a barrier 5 times too tall, trying to escape a trillion times a second, and after 1 billion years it simply succeeds. The click of a Geiger counter is that success made audible. The same effect is in your pocket. Every photo you have saved sits behind a thin wall of oxide that electrons tunneled across to become trapped, their presence and absence writing your ones and zeros. A needle held nanometer above a surface, never touching, traces single atoms by the whisper of current that leaks the gap. In 1989, 35 xenon atoms were dragged into the letters of a company name, and the tool that moved them worked only because particles refused to stay where walls tell them to. In 2025, a circuit large enough to hold in your hand was shown to tunnel as one whole object, and 3 physicists were given a Nobel Prize for it, and it is inside you right now in the dark and warmth of your own cells. A single hydrogen atom bonding 2 strands of your DNA flickers across the bond it sits in, here and then there, a proton tunneling where classical chemistry says it should stay put. Most of the time nothing comes of it. Once in a great while, that flicker helps author a mutation, a tiny quantum edit to the code that made you. Enzymes use the same trick on purpose, squeezing their reactions close enough that a proton can leak through the barrier instead of labouring over it. The chemistry of life leans on the loophole too, so let the shape of it settle now, gently, without any need to hold it all. One quiet effect lights the sun and empties the nucleus. It stores your memories and stirs inside your blood. The universe you call solid is a probability wearing the costume of certainty, and it wears it well. There is a strangeness in that, but it is not a frightening one. It is closer to relief. The wall holds, the sun burns, the floor keeps your weight. Every improbable thing that would unmake the ordinary world stays improbable, night after night, without ever being asked. You do not need to follow the numbers anymore. You do not need to remember which one belongs to the sun and which to the atom. Let them loosen and drift apart like lights going soft on a far shore. The particle does not decide to pass through the wall. It simply spreads out and waits, and mostly stays where you would expect. That is enough. That is the whole gentle secret of a solid world. Somewhere far past all of this, at the very edge of what physics can even ask, the vacuum of space itself may be resting in a low place that is not quite the lowest. Whether it will ever tunnel to something deeper is unknown, and the honest answer is that the odds, on any time scale that could ever touch you, are vanishingly, comfortingly small. It is a thought for the daylight. Tonight it changes nothing. The world you close your eyes on is the world that will be waiting when you open them. Breathe out slowly. Let your shoulders lower into whatever holds you. The atoms in the pillow beneath your head are trembling with the same restless probability as everything else, and they too are choosing to stay. There is nothing left to solve. The barrier that keeps you whole is doing its quiet, faithful work, the way it has for every night of your life and every night before you. Let the wonder be a soft thing now, not a sharp one. The universe runs on a loophole, and the loophole is kind to you. It lets the sun shine and lets the wall stay. That is a good place to rest. Sleep well tonight. Good night.